The fastest way to finish a retrieval-augmented generation project is to keep your vectors right next to your rows. But most AI setups do the exact opposite. They route traditional data, like text and timestamps, into a relational database like Postgres. Then they split the vector embeddings off into a separate, dedicated store. Running two separate data stores means managing two of everything: two authentication models to secure, two sets of credentials to rotate, and network joins to negotiate every time you query them together. The real risk lies in the transactional boundary. If you insert a text chunk into Postgres and its embedding into the vector store, and your system crashes halfway through, you are left with broken synchronization. One database has the record, the other doesn't. For a massive billion-vector enterprise deployment, that complexity is a necessary trade-off. But for a personal corpus or a mid-scale application with a few 100,000 rows, maintaining two distinct databases is over-engineered and introduces unnecessary fragility. This is a single Postgres database node, storing both the text and the vectors together. This is made possible by pgvector, a shared library loaded into an existing Postgres process. It allows you to treat a high-dimensional vector as just another typed column sitting right next to your text. The extension adds a new vector data type and mathematical operators for calculating AI similarity, like cosine distance. Everything else, the write-add logs and the transactions and the query planner, comes straight from Postgres, unchanged. If a write fails, both the text and the vector roll back together. Before we look at the specific performance data that proves why this single node setup works, take a second to like and subscribe. Understanding the benchmarks we're about to cover will save you hours of infrastructure design on your next build. To test how far we can push this simplified stack, we set up a benchmark on an NVIDIA DGX Spark using an ARM-based Grace CPU. The starting corpus is exactly 1,000 news headlines, embedded by a Nematron model. The Nematron embedding model outputs 2,048 dimensions by default, but it supports Matryoshka truncation, a technique where you slice off the end of the vector to reduce its size, while preserving most of its semantic meaning. For a personal scale corpus, truncating down to 1,024 dimensions is a common sweet spot. This chart illustrates the trade-off of that truncation. Dropping from 2,048 to 1,024 dimensions cuts the storage footprint in half, down to just 4 kilobytes per vector, while it only gives up 4 points of retrieval recall in the downstream search. With that dimension size locked in, the ingestion script processes the chunks, embeds them, and streams them directly into the Postgres container. End to end, the stack handles 99 documents per second. With the data loaded, we test retrieval speeds. The standard advice in the AI space is to immediately build an approximate nearest neighbor index, like an IVFF flat cluster or an HNSW graph, to speed up your vector search. But when querying these 1,000 rows, the Postgres query planner actively ignores the complex HNSW index entirely. Even if the index is sitting right there on the disk, the database refuses to use it. At a 1,000-row scale, our 1,024-dimension vector column totals 6 megabytes, fitting perfectly inside the Grace CPU's L3 cache. A sequential loop over that cached memory takes 2 milliseconds. This linear walk is faster than paying the startup cost to traverse an HNSW graph. If you want to see the exact benchmark tables and the open-source code used for this test, check out the ai.fieldnotes website linked below. The planner is doing exactly what it was designed to do. Blindly applying standard AI engineering advice fails to account for how mature database engines intelligently optimize for specific data volumes. Eventually, your application will grow, and that sequential scan will lose its advantage. The mathematical regime shifts somewhere between 10,000 and 100,000 rows. As the row count increases, the cost of checking every single row climbs. Eventually, the logarithmic efficiency of navigating the HNSW graph finally outpaces the raw sequential scan, and you start seeing sub-millisecond latencies from the index. As you scale toward that 100,000 row mark, you also have to manage toast pressure. Postgres stores large data points, like our 4 kilobyte vectors, out of line. Since every distance calculation has to read those tuples, you have to deliberately size your memory buffers to accommodate the growing vector data. A single Postgres table can serve as the unified substrate for several different AI functions at the same time. A second brain queries similar notes. A wiki detects duplicate pages. An agent recalls past research trajectories. all three use the exact same index and the same math. For any personal or mid-scale AI corpus, adding a column to an existing database is simpler than maintaining a dedicated vector store. Now that we have our data, our embedding model, and a unified store, we just need the generator. In the next video, we'll wire a local Llama 3 prompt directly to this Postgres table and complete the end-to-end retrieval loop. See you there.